I want to speak to you about a new organization called the Eco-Modernist Society of North America. I'm here because we are in the midst of a potentially monumental ecological crisis. It is only through a new environmentalism 2.0 that progress can be made. We believe that our only hope for human advancement and even human survival is through the exponential advance of science in the service of humanity. We stand firmly against the war on science that is predicated on the appeal to nature fallacy, which is the belief that whatever is natural must be good and whatever is unnatural must be bad. This belief has become an impediment to advances in areas such as human health, social progress, and even environmental progress. In the field of medicine, the appeal to nature fallacy has already led to catastrophic outcomes. Resistance to vaccines threatens public health and the lives of children. The unwarranted resistance to GMOs has not only held back the fight against climate change, but it has also hampered our ability to feed the developing world as well. Campaigns against GMOs have also held back efforts to ward off the deadly Aedes aegypti mosquito, which has killed countless millions as a carrier of disease and plagues. The scientific consensus concerning the safety of GMOs is solidly supported in every major scientific organization across the planet. The only thing green about being anti-GMO is the extra cash that is made by overcharging for expensive boutique food. But that won't cut it when it comes to raising crops with accelerating heat stress, droughts, floods, disease, and insect infestations brought on by a hotter planet. It makes no sense to accept the call of the IPCC for decarbonization within the next 12 years and yet reject their conclusion that these goals are impossible without nuclear power, which has proven itself to be the cleanest, safest, and most reliable way of achieving decarbonization. It is the most reliable way to decarbonize simply because the alternatives of weather-dependent power sources are inherently unreliable. And nuclear is the cleanest energy source because it is the only form of energy production that completely encases its waste stream. Super safe, advanced Generation 4 reactors, which will almost completely convert existing nuclear waste to centuries worth of energy, are coming very close to commercialization. In fact, it goes completely against most everything we're led to believe. But nuclear is legitimately the safest form of energy generation according to all the accepted worldwide energy fatality data. But there is one thing that nuclear is not safe for, and that is the fossil fuel industry. The fact of the matter is that the fossil fuel industry has a long history of funding the anti-nuclear movement, along with climate change deniers, to protect their bottom line. Solid science is in dire need of a champion. And that is what eco-modernism is all about. Eco-modernism is a new environmental paradigm which looks to reverse the fear of nuclear power and scientific progress in general. Ecology-based modernism is the most direct way to define it. Eco-modernism as a philosophy is described in the Eco-Modernist Manifesto. We believe humanity should not be rejecting technological progress, but rather separate our impacts from nature through the responsible use of technology and urbanization. Urbanization is an unstoppable worldwide trend and the best solution to many environmental problems. It offers sustainable development for the human population and is a historic antidote to both deforestation and species extinction as humans move away from using wildlife as their protein source. Vertical, urban, high-rise architecture minimizes the use of land, resources, and energy, enabling walkable cities that facilitates the more efficient use of mass public transit as well. It must be emphasized that our support for technological solutions is definitely not about defending industrial polluters, nor do we accept funding from corporations or industry. Nor does our defense of technology imply that we just need to sit back and let things take care of themselves. To the contrary, we believe that humanity is at a crossroads that severely threatens our future on this planet. We reject the idea of resource limits on many levels. The advance of science has a long history of getting around problems of resource scarcity and will continue to do so. Another reason is that Earth is just one of a multitude of worlds available to explore in our solar system and beyond. Comets and asteroids are untapped reservoirs for raw materials. If we could find a way to thrive in artificial ecosystems off-world, we could use what we learn to help sustain terrestrial ecosystems here on Earth. I hope by now you understand the worthiness of our cause. Ecomodernism is really only a philosophy at this time. I want to talk to you about the necessity of turning it into a movement, which will be part of the larger environmentalist movement. For it is only through our presence and participation that there can be any hope of moving environmentalism in the right direction. Our aim is not to divide the environmental movement, but rather to multiply its numbers with the incorporation of many scientific and educational communities that is working to both build chapters of eco-modernist societies and support our growth worldwide. We aspire to increase our numbers by bringing together the numerous supporters of climate action that have been alienated by mainstream environmentalism's wildly contradictory support for the shutting down of nuclear power plants in the midst of a climate emergency, and welcome them into our ranks. Thank you.
Please subscribe to us on YouTube, EcoModern channel. Also to subscribe to us on Twitter and Facebook, EcoModern Society of North America.
That's where it stays. Just a word they say. Freedom, just a word they say. Let me tell you something about this world I see. With my own two eyes, 20/20 vision. Let me tell you something, brother, about you and me. Just a word they say. Freedom is in heaven. That's where it stays. Freedom, just a word they say. Freedom, just a word they say. Just a word they say. Freedom is in heaven. That's where it stays.
Hello and welcome to the Eco-Modernist Channel Live. I'm Carl Pauls. I'm here with Gabriel Ignetti and our special guest, Mattias Lantz. Mattias is a researcher in experimental nuclear physics at Uppsala University in Sweden. His research on nuclear data includes the study of radioactivity in the environment. He also teaches courses on reactor physics, probabilistic safety assessments, life cycle assessments, and Monte Carlo methods. He works on ionizing radiation, different aspects of nuclear power, and external effects of the energy. Sorry, that got cut off, and I just realized we didn't rehearse that that intro like I usually do. But welcome,
All right.
Mattias.
Thank you, Carl. It's nice to be here.
Yeah, I just know a little bit about everything like you, and maybe not as much about everything though. And this is really interesting to see. You're talking
I don't
about
think there's any maybe.
you're talking about probabilistic safety assessments. And one thing that is especially significant in the U.S. is sort of the reform of our code and the reform of our licensing process, where instead of a plan for every single fault in a system and a remediation for every single possible fault, we look at the probabilistic outcomes. You want to explain more about that and how it benefits nuclear plant development?
Well, I gave my students one exercise to do it on, like, Hansel and Gretel or Three Little Pigs, to take a small fairy tale. So it's something you call an event tree analysis. You start with one initial event, like something breaks, what happens then? And will whatever system you have after that to take care of this first issue, will that work or not? You have a certain probability for something to happen, and then what happens in the next step if that fails or if things go well. Sort of like a fairy tale. First this happened. Will the wolf break the house for the first pig? What's the probability for that? And then what happens with that pig? Will he succeed running faster than the wolf to the second house, and so on? Or you could look from the wolf's perspective. Will the wolf get fed? Or will you look at it from the perspective of the pigs? Will they survive, and so on? So this is a very screwed way of looking at part of this safety assessment. So each of these steps then, if we look at the house for the first pig, what is it constructed of? And what can make it fail when the wolf tries to huff and puff and blow the house down? I mean, how strong is it? So then you can look at the components in this house, the structure and so on. How was it built, and will it survive? And go down to basic components, and you build something called a fault tree up to a top event, which is the house fails. So you put in all relevant aspects. And the main challenge here is, of course, do you have all the relevant information? And can you assess a probability for all of these basic events? Like, you can be down to bolts and nuts, essentially. What is their strength? What is the probability for them to survive a certain tension, and so on? So if you have all those data, you can build these event trees with Boolean algebra, is what you use, logical and an OR settings, and then you build this up to this top event. And that adds to this event tree, the fairy tale that I spoke about. And then you go to the next event, and you hopefully have data for the next system. And you then get a number of different outcomes where you either succeed, or you have a partial success, or you have a real failure of different degrees. So I'm teaching students about how to model these kind of systems. And so we start with a fairy tale. It's really fun to read the reports, because that is not really a fair assessment. You have magic witches, and you have a lot of not so serious stuff in that. In the real world, it's more constrained. You can find realistic data, but it's fun to see how the students handle that. And then we do it on more technical systems, like a reserve cooling system on a nuclear power plant, for instance. I'm not sure if that was a good answer.
I can't talk a lot about what I know about that, I guess, because I'm not sure what the bounds are. But yeah, this is a very important, strategy to update how we do licensing in the U.S. And I'm glad that you're teaching it. And so this is really exciting to hear. Tell us more about.
I could add that.
Mm-hmm. Go ahead.
Sorry, please go on.
No, no, I was going to move to the next question. Go ahead.
Okay. I mean, this is one way of looking at it, and one has to be careful, because one thing I tell my students, if you give me a response, an answer with 5 digits, then you haven't understood a thing. I mean, because you make assumptions about these values. How realistic are they? Some data you have really good accuracy on, but you have to make estimates. And sometimes in these fault trees, you can also put in human actions. So what is the probability of an operator understanding the situation, doing the right thing, and so on, or having to make in a stressful situation to actually do the right thing? And these things are really difficult to handle, and how do you handle it is part of the game also. So you also have to look at human factors, and I'm not teaching that, but I'm doing it with a professor in information technology, but he's actually a psychologist, so he's teaching that part. And so we do this course together, so they get very different perspectives, and we sort of try to not fight each other in class, but we complement each other, so they realize, okay, the numbers and these probabilistic methods are really important and helpful, but you also need to look at other aspects of this. And you also have what is called deterministic methods, where you look at what is the strength of, let's say, a bolt. When will it break? At what tension is it designed for, and so on? How high is a levee when you have a flood coming? How much water can we take during a flood? And so on, and so on. So many perspectives that you need to have at the same time, and be able to not stare blindly at your method of favorite choice, because other perspectives may also be very important in order to get a broader picture. And as we know, if you look at the numbers for the probability for a nuclear meltdown to happen, people refer, but it's like once in 100,000 years. We have had a number of nuclear meltdowns. So things were not considered in the models. Or even if the model was quite accurate, there was still something else happening that relation between different systems and so on were not fully modeled, and so on. So you cannot trust them blindly. They are really helpful, and you can learn a lot from them, but it's not the entire truth.
Right. Gabe, you have a question.
Yeah, I don't know if this is in your wheelhouse, but you said, like, these emergencies, they're tricky. Could that be automated? The response, so it's just out of the hands. Just press a button. We got this going on, and the computer will figure it out and act.
Well, many things are automated. Like in the philosophy when they built the Swedish nuclear power plants in the 70s and 80s was that it's called the 30-minute rule. The operators they shouldn't need to do anything within the first 30 minutes. Reserve systems should go on automatically for cooling and so on. So they have peace and quiet to think what is going on, what should we do next, so that they can discuss and so on. So the system is automated even with 1970s or even 1960s technology. But now, of course, with modern technology and AI and so on, maybe you can use a lot of sensors and data in a much more clever way. On the other hand, how much IT do you want to put into nuclear power plants also? If you have that, there's one concern, will somebody hack this? Or you will have a random error in a complicated computing system where, we have a lot of automatic sensors now that were analog before. And that is one thing driving the costs for new nuclear power. If you put in a new thing that is digital, you program it to do a certain thing. The regulatory agency really wants you to make sure that you can show that it will not, by chance, start doing something else than what the purpose is here. So there's a balance here. We also have a challenge with young people now. People in my age, we had like a moped or something, a small motorcycle, or you were fixing with things. Kids these days don't really, usually don't live in that environment. And just a faucet in the bathroom, you used to have hot water, cold water, and everybody had a built-in feeling for what is turning something on or off. Now we have this thing in the middle, and kids don't have a feeling for this, and so you have to teach these. There's a lot of silent knowledge where you get newcomers in and you assume that they know these things. So it's important to be aware of that they don't have this information. They need to learn things that everybody knew before. Mm-hmm. And when you have a reactor that is pushing for 50 years, where you have old technology, and do you really want to change it into this digital thing? That is one challenge. And then keeping the old stuff, and you have young people coming in who don't recognize things that were basic for those who designed it. So there are many challenges there with information transfer, and some of it is silent knowledge that it's not so. You need to experience it, and to enable people in the nuclear industry coming in to learn through experience is very important to get to know the machine and all its aspects.
Really, really interesting that we have a different class of tinkerer these days. Instead of the moped, you have an electric scooter, and instead of tweaking the carburetor, you're tweaking the controller code and downloading operating systems onto your bike. And so it is a different application of technology for sure. There's a new knowledge and a new intuition about technology that is almost alien to traditional knowledge. And I like to sit on that edge of, the generation I am. I've been exposed to both, and it's interesting to watch the changeover happen.
Indeed, because my kids who are teenagers, I mean, for them, this always existed. It comes natural for them. Maybe they don't know. Well, we try to get them to start learning how to program things, but it's not really catching on. But to understand what's going on in the machine on the basic level, because they have so many things on the top layer where they can do so many things that I could never dream of when I was a kid. And this enables a lot of new possibilities. And this is also, sometimes I feel like I'm very conservative when it comes to the progress for new digital applications in nuclear power. That it's my lack of imagination maybe of what we can do with this, but the hard physics still remains. You need these pumps and valves and a lot of concrete and stuff, and that is hard physics, which is quite analog and maybe boring for my kids, but it's also essential.
Yeah. Do you want to tell us anything more about your work, the courses you're teaching, your research?
Well, my research is we play pool with accelerators and atomic nuclei, to put it simple. So we accelerate protons, for instance, into some target, or neutrons. Neutrons you cannot accelerate. You need to create them by accelerating something else and break them out from a source of some light material, for instance. Or you can do it on a heavy material like lead. We have these spallation targets. I think there's one being built in Michigan as well, where no, they're not doing that, but where you shoot protons on a heavy target, and you break the nuclei, so you get a huge flood of neutrons out. 30 years ago, it was fashionable to do research on accelerator-driven reactors. They would be subcritical. So they would not self-sustain the reaction without having extra neutrons coming in from the outside. So you would have an accelerator which would break up neutrons and lead atoms, and you would get an intense field of neutrons adding to the neutrons you have in the core already. And in that way you would run it. I think there was one project in Los Alamos on this, for instance, and there was one at CERN in Geneva in Switzerland. And other groups in Japan and Russia. There was a Swedish group also working on this. So the idea was to build a subcritical reactor where sort of the advertisement was, well, if something goes wrong, you just shut off the accelerator and then you will not have a meltdown. But of course you have the same problems. You have caused a lot of fission, so you have a lot of fission products that will release heat. So you still need to cool this reactor like another reactor, but it has some interesting features. And there is one project actually going on in Belgium still on this. Most of the science world moved into fast reactors instead. But there's one project called Mira in Belgium where they intend to push for this. And it's nice to see that is going on. It will not solve all our problems with nuclear waste or energy, but it's one interesting concept, and I'm happy to see that research is being pursued on it. Mm-hmm. That was my entrance into this field, to do research on if you shoot something and collide with an atomic nucleus, what will happen? What is the probability for a certain reaction to happen? We have models for this, but we can also measure to see the probabilities for different kind of reactions. So I've been participating in a number of different experiments where we play pool with atomic nuclide and see what happens to add to this multidimensional puzzle with where we need nuclear data in order to run a nuclear reactor, to understand what happens in a supernova in astronomy, or how to improve medical treatment with where you use radiation, for instance. So nuclear data can be used in a number of applications. So that's where I started my career.
To iterate for the audience, this is what you're describing, playing pool with the subatomic and the atomic is, in essence, the data behind a Monte Carlo simulations. Is that right?
Yes,
And
indeed.
so you are taking this experimental data and refining the simulations and the Monte Carlo methods that predict how nuclear physics itself works. And what's the state of the art of these models?
Yeah, and I'm not doing all these steps. I participate in some experiments, try to add to the database. Then we have nuclear data evaluators, and they use nuclear physics knowledge. They use the data. They are usually very good at statistics. And until recently, I would claim that they also added a bit of black magic into what they're doing, because it's sort of a general feeling for what is, by knowing the models and also to know how they vary between systems, and especially when you have limited data in certain areas. We cannot measure everything, because if you look at a nuclear reactor where you're down to thermal energies and you start with neutrons that have several mega electron volt, we have, I think it's 9 orders of magnitude difference. So you go from milli electron volt is the unit up to mega electron volt. So yeah, that's not a factor 1 billion. You cannot measure every single energy in between, and you cannot measure for every single nuclei that may be in a nuclear reactor. So you have to do good measurements. A lot was done when, well, first we had the Manhattan Project and atomic bomb. They measured some data to understand that process, but then for nuclear power, there's been a lot of measurements going on in the 50s and 60s, and that is good enough for any regulatory agency in a country with nuclear power to say, this is good enough, we allow you to run a reactor. But if you want to improve, sort of, maybe we have too large safety margins in certain areas, or there are certain decay processes where we know that we get decay heat and we need to understand the time scale of it, or how much heat and so on, then you need more data. So we try to select measurements that we can do. First, we need to have a good accelerator facility and a measurement equipment. We need to find the suitable targets. We would like to measure 1 plutonium, and just to get hold of enough plutonium to make our kind of measurements worthwhile is extremely difficult. They have a lot of legislations on that. We go to a lab in Finland, and we wanted to bring in a new target of uranium with uranium-235. But they already have enough fissile material for what this whole lab has permits for. So something has to leave that lab before we can bring our target in, and so on. So there are many challenges just to get the experiment going. So you cannot measure everything. We try to do measurements on some things to add to this puzzle where you have, it's like a jigsaw puzzle where you have many blank spots. So you have to try to figure out what is the general picture. This is what AI is doing quite cleverly now. And some people try to use that here also in different ways. But in the old days, there was a piece of black magic when the evaluators tried to put this data together. And now they can use a lot of powerful statistical models and good computing power to do this. But you still need to have a good feeling for it. So I wouldn't trust anyone say, I have the best AI model here to create all this evaluated data to improve and cut the corners on safety margins and so on. I wouldn't trust that. You need a good person doing this who understands the physics of it and understands statistics, and to understand, that there are tricks in this that are not always so easy.
I want to bring us in context. Some of the rhetoric against nuclear energy is commonly something like, well, once you put that in the environment, who knows what will happen? We have no idea. And so if you could give us a sense, both from this macro historical record sense, and as well as the low level, the intricacies of the interactions, do we have our hands around the basic idea of how radiation works?
How radiation works, or the nuclear physics, is sort of, well,
Yeah.
it's related. So yeah, I'd say we have a really good idea. And at the same time, when you go from the physical part to, let's say, biological effects of radiation, there we have a lot of knowledge, but there are also areas where we really don't know clearly what happens, like in the low dose region, for instance, which is, of course, always controversial. And to make a simple answer would be, we have more important things to worry about than what happens in the low dose region. This is my general simplified answer. But from a research point of view, it's of course important to try to find out better what is happening at low doses. And then when it comes to, yeah, you can speak about doses also inside a nuclear reactor, where you have neutrons impinging on structural materials. You want them to interact with the fuel, not with the reactor vessel and so on. But that happens. So, I mean, there's a lot of research going on that also. When do things become complicated or problematic there? And I would say we have a good data set. We are, and it's continuously monitored as well. So it's rare that a regulatory agency would say, we don't know enough about this. It's more, they want to push for more research to understand things better. And if it comes to the data that we are measuring, this long chain from measuring something, publishing it, having some model makers look at it, trying to improve their models, then having an evaluator looking at this and using it and saying this is the best database we have now, the best knowledge. We can have that, and still you need to convince a regulator that, now we can sort of cut the corners on these safety margins because we know things much better. A regulatory agency will be very conservative and will not just, now you can run without checking this, or you can, sort of cut certain corners, which they wouldn't do that. So it's a really long process. So we try to add to the database, but we do not expect quick changes in how a regulatory agency would act, for instance, or that all those reactor concepts that are being researched by different groups now, whether it's a molten salt or an accelerator-driven system or a lead-cooled reactor, we try to add data to that, but it's not like it will change their strategy and what they're doing now. If you are evil-minded, you could say that all my research is worthless then, because, but the good news is we have good enough information to do this, but we can always learn more and maybe do it better in the long run. So it's a marathon run. It's not we want all the data at once, of course, but we will never get that. So we try to measure new things, and maybe one thing that is more important than actually finding better safety margins on certain nuclear data is that we educate people. We have doctoral students, we have master students involved. They learn things, and then they go out in society, whether they will work in a nuclear power plant or in research or at a regulatory agency. They have a lot of knowledge and experience. And maybe that is more important than the actual data that we sometimes measure, because that can seem a bit esoteric to most people, what we're measuring.
Gabe, why don't you take a question, and then I'm going to go into the future of nuclear.
Okay. Well, I was kind of headed into that anyhow, because you mentioned about the lead reactor. I mean, there's so many designs that I've heard, but the only thing that it seems that has cachet, other than the small modular reactors, but I mean a total different design, is the MSR. Does that rule out these other reactors, all these other reactor designs, or why is everything headed, everybody talking about just that? What about these other designs?
If you talk about a fast reactor, you usually talk about a lead-cooled reactor or a sodium-cooled reactor. There have also been reactors running on mercury, for instance, I think was used in one American reactor that produced electricity, if I remember correctly. So different methods have been used, and the Russians were really good at running lead-cooled reactors in submarines, this was during the Soviet Union time, and so they sit on a lot of experience. And after the fall of the Soviet Union, and I'm sort of deviating from your original question here, Gabe. I will try to get back. But a lot of groups try to do interaction with Russia, both to learn about this, but also there were a lot of funding going into Russia for research projects. There was a concern that some of these really excellent Russian scientists would go to Libya or North Korea or something when in the early 90s, when the Soviet Union had broken down and Russia was in a deep financial trouble. So we had a group in Stockholm that was quite involved in some interaction projects, and then one day it just stopped. So they didn't want to interact anymore. European Union had several research projects also interacting with Russian groups, and then the Russians said, no, we don't want this anymore. So the Russians probably felt they just want our information about lead-cooled reactors, but also, as we know, the government has had another agenda also. So there is a lead-cooled reactor project probably going on in Russia. On a European level, there was something called Alfred. I'm not aware of the present status. Probably it's quite on hold. We had Astrid and Alfred, where Astrid is a sodium-cooled fast reactor and Alfred was a lead-cooled. So these were two main fourth-generation reactor concepts that were being pushed at the European level. And the group in Stockholm, there has branched off a company called Lead-Cooled. So one of the professors started this. So from what they've done some material studies also to find corrosion-resistant metals. So they have a concept that now, together with parts of the Swedish nuclear industry, that they will build a test loop. I think this spring they will actually have sort of the big first shovel in the ground to build this test loop. It will be non-nuclear, but just to heat up liquid lead and see how it performs with cooling aspects and how it interacts with materials around and so on. So that's two things going on. We have sodium-cooled reactors. There are two running in Russia. We have one outside of Beijing in China. India is building one, and Japan hopes to get back this Monjud reactor that had an accident in 1994, and then it took them forever to get it up in shape again. And then after the accident in Japan in 2011 in Fukushima, they had another incident at the Monju, so they shut it down completely. But there are prospects for a new sodium-cooled reactor there. France had this big Super Phoenix, which was a 1500 megawatt electricity reactor. That was a really big project, but it was cancelled in the 1990s. And those involved say, it was just the political reasons. But if we try to see a balance on it, the costs were running, and they were not able to convince the politicians that the government should put in more money in it. We also had, of course, all the EBR 1 and 2 in the US that were sodium-cooled. Mm-hmm. So molten salt reactors is a different concept, and it, as far as I understand, it's usually a thermal reactor, not a fast reactor. When it's a really nice concept. You don't worry about having a fuel meltdown because the fuel is already molten, and then you pass it through a region where the reactor sort of occurs, where you have where you can get the chain reaction going, and the fission products, the garbage that you produce, you filter it out online. It's a very elegant solution, but and there are some groups working on that. I'm not sure about the status in the US. I'm sure there are groups talking about it, but we have one group in Denmark, of all countries. Denmark has always been very anti-nuclear, but we have two companies working on nuclear power projects there, and one is for a molten salt reactor. So I haven't really answered your question, Gabe, and I'm sorry for being long here in my response, but there are some projects on molten salt, but I don't see that it's either or. And I probably, when we talk about small reactors, the first ones will be with light water. It will be small pressurized or pressurized reactors or boiling water reactors. But then we have lead-cooled, and we may have some molten salt reactors that are also interesting concepts. And I hope to see several of them flying. But I'm quite sure that the first ones will be water-cooled, and probably that will dominate in the near future, if they fly.
So let me paraphrase that a little bit and tell me if I'm wrong. Is that it's possible that as this lead technology matures, that it might prove to be better than sodium, and that's why they're still working on it. Would you say that kind of paraphrases that?
You mean lead instead of sodium? Well, I'm not sure. They both have nice aspects from a safety perspective that you do not have with a light water reactor, because in a water reactor you need to have high pressure. You can run both the sodium reactor and lead reactor at almost normal atmosphere. So you don't have these huge pressure gradients to worry about if something breaks. And also the metal can transport heat away from the cores, and you can get this self-circulating cooling mechanism just through heat transfer to the metal that will start moving by itself and transfer heat. So, and it does that much more efficiently than water does. So you have a number of very nice safety features by having a reactor with lead or sodium. And sodium is complicated because if you get water nearby, somewhere you need to convert the heat into steam in order to turn a steam generator. So you don't get rid of that, but so you need to have the conversion from sodium to water, and you have heat exchangers, and you probably have double sets of those, which you may lose a few percent then of the efficiency of doing it in several steps. But it's really important. You don't want sodium together with water. If you remember chemistry class in school, the teacher dropping sodium into water, it's quite.
Yeah. Could I ask another question? Because you're going on to future nuclear. And this seems to be in your wheelhouse. And, I hear from anti-nuclears a lot about wind scale Sellafield and the great expense of cleaning it up, the great expense of cleaning Fukushima and the others. I mean, knowing the real, having more of a grasp of actually how bad radiation is and all of that, what would a rational response or cleanup cost, and what would it look like?
Wow, tricky question. I mean, the handling of a nuclear accident where you spread radioactivity into the environment and consider if you should evacuate people or not, I mean, it becomes as costly as the country will afford it to be or will set a level. This may be a strange answer, but I remember a discussion I had with an expert at the Swedish Radiation Safety Authority, because I was concerned that for cesium-137, which is this 30-year long life, the half-life is 30 years. We have a lot of cesium in mushroom and in wild boar and in the ground in Sweden after the Chernobyl accident, which is almost 40 years ago. So we do projects where we measure that in wild boar, for instance. I spent 2 years grinding boar feces. I'll try to keep a clean language here. I didn't see this as a career move when I went into nuclear physics, but it's a lot of fun as well. And you can put on a podcast and you stand there grinding things and prepare your samples. And then you go to the computer and you do something else with nuclear data and so on. So I have a diverse job. But we have cesium-137 that puts a limit on, according to regulation, how much are you allowed to eat? There are certain limits. And when the accident in Japan happened, they set a very strict limit. And why do they do that? That's a really unnecessary cost. Because they throw away, not the least, rice that you could sell it in Europe, because our limit for when you're allowed to sell it is much higher than what they put in Japan. And this guy from the agency, he said, well, they can afford to do this. So it's a cost-benefit analysis, a risk assessment being done here. Because the risk, according to the model, we have this linear no-threshold model that I assume that you have discussed it in the podcast before. So if we assume that one is correct, that is what all the regulatory agencies are using. They may have different risk factors there, or set a limit that is different in different countries, depending on how important is it that we go on with in Sweden and Norway, we had reindeer herding in the northern Sweden, which was affected by the Chernobyl accident. So we had a certain limit of how many becquerels per kilo of reindeer meat were you allowed to sell. And the limit in Norway was much higher because they valued the meat more than the eventual risk for human health. This may sound cynical, but we do this all the time. We have what is the cost of a human life when it comes to traffic or malfunctioning in medicine or whatever. We do it all the time.
Cholesterol.
Sorry?
Cholesterol.
Yes, putting certain things into your sodas or whatever. So, and it's based on models and assumptions, and we don't, at these low levels, it's really difficult to say that there really is an effect. But we base it on something, and then it's up to each country to decide, is this a good enough level or not? So in Japan, they had the government had lost credibility. The nuclear power companies who boasted that we are the safest in the world, they lost all credibility. So probably it was a way for the government to try to regain some credibility to say we put a really strict limit for how much cesium there can be in our food. And they can afford it. So it was important for them to put this limit. But you get into these situations then when something is close to that limit, people will feel concerned, not being aware of that, okay, the level in Sweden is 3 or 5 times higher for the same product. And so you get a lot of weird effects there, and you can get media reports, we had so and so many samples that were above the limit. Yes, but nobody talks about the risks because that is complicated, and to understand these risk models we have, this linear no threshold model that I'm waving here. So so then when it comes to evacuation, like there have been several British studies. There's a British group that looked at this. There are some peer-reviewed papers, and I need to look closer at them. And their conclusion is that both in Fukushima and after Chernobyl, too many people were evacuated. In the immediate phase when you have a number of short-lived things, and also you don't know what will happen next while the accident is going on. It's a wise decision maybe to move people. But then, even though we were above this 20 millisievert, which is sort of a limit of how much dose per year you can get from a human-caused accident, this British group argues that, the risk of staying is lower than all the negative aspects of moving people. Now we don't talk societal costs of people having to have a new place to live and other things and the sanitation, but just the health effect of people, of feeling like you're a victim and you're moved, you're away from your home, your whole reality. We had farmers who committed suicide because maybe this farm has gone for 7 generations, and all of a sudden you have to leave. You leave your cattle and your land and everything just overnight because the government says you have to evacuate because this is too high radiation level. Some of these people would live and thrive and probably have a good life and live until they're 95 if they had stayed. But it's really difficult to argue that, we have set a certain limit and then we should say, no, this limit doesn't matter because we have some British scientists who calculated that it's a better benefit for them to stay.
Well,
it's difficult to backtrack.
It is, unfortunately, the reality that, especially in America, we had the plant at 3 Mile Island, which released some radioactive inert gases, and we evacuated tens of thousands of people for this. And it is host to not only enormous number of conspiracy theories and speculation about the effects, but also the real effect of that accident was entirely economic. It was entirely based on the decision to evacuate with incomplete knowledge. And that's the fear of radiation has, if you feel well informed, it seems to me that you will easily make the decision that it is possible to kill people with fear
Indeed.
when no harm would have come to them. And what in policy we have to not only communicate this, but make the right decision about risk. So we of course we'd be very happy to speak with experts on like the low dose experts and even the moderate dose, like Geraldine Thomas of the Chernobyl Tissue Bank is an excellent example of a person who has expertise in this field. But it doesn't seem to me like as you said, low dose is not worth studying. And how do we square that with sort of this big policy question? How do we decide that, well, it's worth not using nuclear energy because we're too lazy to look at the data? It seems very defeatist.
Yeah. If I'm a rigid scientist and what do you call it? We have this British alarmist, Chris Busby. Maybe you heard of him. He calls people like me stupid physicists. And okay, let's be a stupid physicist. Just think about what we know and the factors here. Then we have the human factors and how to convince that this physics knowledge, what we know, and also being aware of that there are some things we don't know. But the assessment here, when we evaluate everything, it's better to do this than to do that. Just overall, I mean, there may be a slight risk that we don't have all control over, but that risk, if it's real, is still much smaller than other things that we take for granted every day. I mean, we have around 10,000 people dying every day from the normal use of coal, gas, and oil in machines that works perfectly. To compare that with the Chernobyl accident, where it's reasonable to assume around 4,000 extra cancer deaths over a time period of 80 years. I mean, the numbers do not compare, but that doesn't mean that Chernobyl was just not important. I mean, it was an important event, like it or not, and we cannot get around it. We have to handle it and be aware of it and sort of assume responsibility for it if we want to continue with nuclear power. We need, it's part of the discussion. We can't get around it, but it takes too much of the attention. We shouldn't forget about it, but it should be a small part of the discussion. And as soon as you start talking about nuclear power, what about Chernobyl? Yeah, I mean, we can talk about that as well, but there are so many other things to talk about. Right. And we compare them with the ongoing disaster with roughly 10,000 people per day, day out and day out, year after year dying. So, I mean, yeah, the numbers don't compare. And the three of us here can calculate that and understand that. But then we have to convince people that, there's no excuse for another Chernobyl, and it won't happen. We had Fukushima with no recorded deaths when it comes to radiation. I mean, they have one or two persons who worked there that got cancer for whatever reason, and they are put in the protocol as this was work-related, which I seriously doubt. But it was still a bad accident, and it could have been an industrial accident where people didn't have to move. But in the initial phase, if we had better understanding, I still see that it would be difficult for a government to not recommend people nearby to move, especially in an ongoing long term. I mean, this went on for weeks and we don't know what happened next. I mean, it was the ultimate disaster. The only thing that didn't happen was Mount Fuji having the volcano there. And I mean, it was the perfect Hollywood movie with Bruce Willis coming in, tearing off his t-shirt and putting in the last control rod to save the day. I mean, it had all the components. And but it was a terrible incident for those who were there. And then when it comes to low dose, you have to stop me, Carl.
In the middle of something, okay?
I got it.
Sorry?
No, I saw Gabe was taking a phone call and forgot to mute.
All
so
right.
I'll make sure that he gets unmuted when he's back. But
Sorry.
Yeah.
I have one more aspect on this with radiation. So when people say, because we also had this thing in Japan where they had been talking about 1 millisievert, and that is sort of the extra dose that society can accept from artificial radioactivity, like from activities like nuclear power, what you get from medicine and so on average. and that was not communicated very well. So people heard, 1 millisievert. You said that was the limit, and now you say 20 millisievert is okay. So how do you communicate this? That in an emergency, then there are other rules going happening, because you have this in other kind of emergencies also, that you need to have a different scale when something happens. Sometimes it depends on the situation, and so when you then have a fixed number like 1 millisievert, and then you talk about 20 millisievert, and not communicating this, which is a tricky subject to most people about radiation, that is difficult. So I hear a lot of people who are pro-nuke saying, but people should have stayed, and I mean, they can live there if it's up to 20 millisievert. So let's say it's 18 millisievert per year, and I know that the extra risk is not very high if it's real and so on. And most of my friends and colleagues know that. But how do I feel about staying and living, that my children are living there, that they are playing in the grass or having a normal life? Will I feel comfortable with that, even though I can do the calculations? I mean, this is not so easy. I mean, and this radiation ghost that we are, that we've been surrounded with since 1945, it's very difficult to just get rid of it.
You can be pro-vaccine, you can be very scientific, you can be rigorously minded, and when it is your child in front of you and the doctor says, or we can do the modified schedule, you'll take the modified schedule. And so that's sort of where you have to have emotional distance from the issue, unfortunately. And it is like we have to really look at the data and avoid that trap. But we can set advisory levels, because an advisory level is well under the known safe level. And still, the advisory levels could be too high. And so that's a little bit of how I sort of square those two facts with one another. So we are running out of time, and we've had a wonderful discussion. Let me hit some high notes of what do you think the future of nuclear power and nuclear regulation is in Europe? Is it the fact that Europe follows what the U.S. is doing, or is it independent?
Well, when the Nuclear Regulatory Commission in the US is doing something, all the regulatory agencies in Europe tend to look at that. And if there are certain new things coming in, that will be considered in the European countries as well. But then it depends. Each regulatory agency in Europe is also different from each other. They have something called WENRA, I think it's only a European thing, West European Nuclear Regulatory Agency. It's a club for regulatory agencies where they try to discuss things and try to harmonize things, because each country started with nuclear power in a different way, with its own history and its own boundary conditions. So the regulations are very different in each country. So they try to harmonize certain things, and now under the present government in Sweden, that is very pro-nuclear, they also put a new mandate on the Swedish regulating agency to also look for, can we harmonize things when it comes to not having to look at every nitty-gritty detail of a reactor that eventually should be built in Sweden that has already been built somewhere else. At what level and what detail do we really need to look at every nut and bolt and so on, in order to see, can we speed up the permission process of building something without risking anything on what is considered reasonable risk assessment level. So yeah, there are things happening, but everybody is looking at what's happening in the US, because then NRC is the big elephant, for good and for bad. And especially since most countries use reactors that are built, can be other companies, but it's all based on licenses from either from GE Hitachi with boiling water reactors or from Westinghouse with pressurized water reactors. Almost all nuclear power countries having light water reactors, except Russia and the VVR system, and also the Swedish reactors, which were built without having the license. So we have issues now, like I think it was the Czech Republic wanted to strike a deal with Korea about building Korean reactors. And Westinghouse said no, because the Korean reactors are built on the license from Westinghouse, and Westinghouse wants to protect its financial interest here instead of, come on, guys, let's build something. But that's at a company level. So the regulatory agencies are trying to, in several countries, are trying to make things easier if possible. At least they are looking at it, and that's a positive thing.
Great. And now this might be a little more opaque, but do you have any insights into how Western policy is impacting China, Russia, India, or vice versa?
I have no clue.
Okay.
But one thing that dawned on me quite recently is that, I mean, China has not developed any new reactor by itself. It's all built, everything they have. They've had foreign companies coming in. They invited everyone to come and build something that they want to, everything except boiling water reactors. They seem to have a hang up on that, but they're testing everything. Also in generation 4 reactor concepts, they try a number of things, which is really interesting. But it's all based on licenses from other companies that are not, it's not developed in China. It's either from Russia or derived from the American companies, what they did originally. And then they have the deals that they can sort of take over this after a couple of years, and they just add a C. Like we have the AP1000, and they are building the CAP1000, which is an AP1000, but they've learned how to do it by having companies coming in and building it, and they're allowed to do it in their own name, and they will start exporting this to other countries. So they are, of course, affected of what happened, but they are running their own game, and exactly where this goes, I don't know. And I don't know anything about what the regulatory agency there is doing and how the Western world affects their policies. I think they feel mature enough to do their own show, and they're clearly showing it by building so many reactors.
I'd be very hopeful to learn that China has a mature regulator, but unfortunately, it is very opaque. And maybe that is a sword that cuts both ways for the West. Is like when we have a advisory notice, this becomes a great international controversy. And even when the Taishan reactor in China had a internal leak, this was blown up and had misinformation created about it, saying that it was a external leak. And so this is it's a problem, I think, in the West, that we allow one kind of information to be turned into misinformation, but we value free speech, so it's difficult to it's difficult to do otherwise.
That's one example I also have of concern. What happened there? Because we don't really know. They haven't spoken about it. The French were concerned, but nobody really speaks up. Then we have another example when the AP1000 was being built, and it turned out that some design was really flawed, and the Chinese regulatory agency was really sharp about this is not serious. And the way they formulated it was like, okay, I mean, Westinghouse should have done their homework, and they hadn't. I mean, it was some engineering issue that delayed the project for a couple of years. I won't go into details because I don't know them good enough, but just the way they messaged that, I felt, okay, they take this seriously. They also paused their build-up program after the accident in Japan a bit to see, okay, are we missing something? So these are promising things. And now they have a lot of operating experience. They have, in a couple of years, I guess they will have more reactors than the US has, and they're passing France quite soon here. So they are keen on running this well, but it is a dictatorship, and what are they missing? I mean, we would like them to be a democratic country running this, and also, are there things we don't hear about that are really concerning? I don't know. But so they're both good and bad examples here, I guess. I would like more transparency on the Taishan incident. What really happened? Now it's up and running. Everything seems fine, but they could be transparent about it.
Yeah.
We need to learn from each other.
Right. Well, it has been a wonderful conversation. Maybe just a few minutes left. Do you have anything that you'd like to promote, anything you want to talk about, introduce us to next steps, advocacy in Sweden? The floor is yours.
Well, when I speak to public, sometimes I start with showing a speed sign from the road, like let's say 55 miles per hour is the equivalent velocity in the US. I usually have a 70 kilometers per hour sign that is sort of a standard velocity on average size roads in Sweden. So I start with that. And when I talk about radiation and nuclear power, I start with showing the radioactivity symbol and what does this make you feel and how do you react to it. And then I say, well, to me, it's like this speed sign in traffic. Because I turned 18, I am allowed to take the driver's license. I have taken the driver's license. I'm allowed to pass this sign in 55 miles per hour in a car. And I can bring one of you in the car. I'm allowed to do that. I can even bring small children in the car and pass this sign in 55 miles per hour, even though they are not allowed to drive themselves. And in the same thing in my lab, we have a radioactivity warning sign here. And if I go to certain labs where there are high radiation levels, I have the driver's license, so I know how to act. I know that I should look for other information, and I also have the education to understand what to do. And I can even bring my kids into some of these labs because under certain conditions, they need to have the child seat maybe or whatever, the equivalent. They can come and visit some of these labs and see things also. Not all labs, not all areas where there may be high radiation, but I can bring visitors to some of these labs because I know what are the risks, how should I act, and I can tell them, don't touch that, stay here, I will show you something, and so on. So sometimes I forget about this, that I have the driver's license and most people don't when I talk about radiation or about nuclear power. And I mean, this is the challenge. You try to help people here to get the driver's license by having this podcast. I mean, it's a nice thing. But we tend to forget. We sometimes think, but people are so stupid. Why don't they get this? I told them the numbers. Yeah, but most people don't. They are happy to be finished with calculating things after they finished high school because they do other things at work. So just trying to, so I try to remind the audience that I'm a nerd and I try to talk with you guys. But if I forget something, raise your hand, take issues with what I'm saying, object to things. That can lead to an interesting discussion, but also I want to make them sure that they feel that I'm not up here somewhere and don't worry about their petty concerns about radiation, because this is a tricky field, and the only way we can sort of win followers into this or have a better understanding is to be aware of that. For most people, this is, if it's not black magic, it's at least scary and something uncomfortable, because this is what they are flooded with all the time. So we are working upstream all the time. It's difficult, but it's a lot of fun to try to make more people understand a bit more about this.
Wonderful. Thank you so much. This has been the Eco Modernist Channel Live. We are live every Sunday at 10 a.m. Pacific. And then what is that? Oh man, my brain is going. We're live at 10 a.m. Pacific, 1 p.m. Eastern. You can find us on Patreon to please support us at the Eco Modernist Channel. You can find us on YouTube at Eco Modernist Channel. You can find us on Twitch at my personal Twitch, which is Soyaddle or soyaddle.tv. Find us on Facebook at the Eco Modernist Society of North America and online at ESNA.earth. That's ESNA.earth. Remember, emissions first, peace and justice will follow.
I want to speak to you about a new organization called the Eco-Modernist Society of North America. I'm here because we are in the midst of a potentially monumental ecological crisis. It is only through a new environmentalism 2.0 that progress can be made. We believe that our only hope for human advancement and even human survival is through the exponential advance of science in the service of humanity. Ecomodernism is a new environmental paradigm which looks to reverse the fear of nuclear power and scientific progress in general. Ecology-based modernism is the most direct way to define it. Ecomodernism as a philosophy is described in the Ecomodernist Manifesto. We believe humanity should not be rejecting technological progress, but rather separate our impacts from nature through the responsible use of technology and urbanization. Urbanization is an unstoppable worldwide trend and the best solution to many environmental problems. It offers sustainable development for the human population and is a historic antidote to both deforestation and species extinction as humans move away from using wildlife as their protein source. Vertical, urban, high-rise architecture minimizes the use of land, resources, and energy, enabling walkable cities that facilitates the more efficient use of mass public transit as well. It must be emphasized that our support for technological solutions is definitely not about defending industrial polluters, nor does our defense of technology imply that we just need to sit back and let things take care of themselves. To the contrary, we believe that humanity is at a crossroads that severely threatens our future on this planet. I hope by now you understand the worthiness of our cause. Ecomodernism is really only a philosophy at this time. I want to talk to you about the necessity of turning it into a movement, which will be part of the larger environmentalist movement. For it is only through our presence and participation that there can be any hope of moving environmentalism in the right direction. Our aim is not to divide the environmental movement, but rather to multiply its numbers with the incorporation of many scientific and educational communities that is working to both build chapters of eco-modernist societies and support our growth worldwide.